Hello, my name is Pedro Otávio. I am a fourth year undergraduate at IBUSE, and my poster talks about means to solve a well-known problem when dealing with a singularity whose Jacobian has non-real, complex, conjugate eigenvalues. The problem of splitting centers from Foucault, with the spotlight for quadratic systems. Before we start, here's my email if anyone wants to read the writing and or ask something. First of all, we can brand the origin as one of three things: a center, a center focus, or a focus. And by this theorem right here, from this book, these are the only outcomes in the case we are dealing with. The definition is not a good mean by itself, so we need to find another one, and this will be done by first writing the components of f like this, changing the system to polar coordinates to get this, and then writing r as a function of theta. This can be done all the time since the derivative of theta never withers due to the even meeting of f2 to 0. After doing this results in equation 4, where you can clearly see that r is written as a function of theta and its derivative is given by a certain map r that takes both theta and lowercase r as inputs. Just to top things off, phi here will denote the solution with respect with the starting condition, with the starting values theta 0 and r 0. Now, after getting equation 4, we can move on to some results from Andronov, from this book, which will help us craft a similar map to the first return, and it's called the aftercoming map. At first, it is set for a given theta equals theta 0 being starting at the origin. However, later, theta, this way will be taken as the theta 0 equals naught. Along with this map, we can also craft the shifting map by this rule. And this is the map that we're going to use to get the behavior of the origin, as can be seen in lemma 7, where each of the three behaviors is linked to the number and spread of the displacement map's roots. This number and spread can be better studied if we know what values the derivatives of such a map take at the origin. These values of the derivatives are what are called the focal values. So, to get the best result, we are going to change our focus to analytic fields. Though the results of the book are broader, they are true for even C1 vector fields. When applying Taylor's formula with Lagrange remainder, we find that the first knotless value, which is called the Lyapunov score of the origin, always happens at odd spots. So no second focal value being knotless. It's always the third, the fifth, the seventh, the ninth, the 11th, and so on. And it can by itself tell the whole story. As seen in Theorem 9, an analytic system does not have a center focus, and if the Lyapunov score that doesn't exist, aka all focal values are null, we will call the origin a center. If there is such a Lyapunov score, it will be called a focus. If this Lyapunov score is positive, the focus will be set as drawing or steady, and if it's negative, it's going to be it's positive. If it's negative, it's going to be steady or drawing. And for positive, it's going to be withdrawing or unsteady. To calculate these values, we need to first expand the map uppercase r in its power series of lowercase r, expand the solution phi with respect to its power series in the starting condition r0, then take both of these expansions and put them on equation 4, and this will yield this expression, which is an equality of power series. From comparing coefficient to coefficient, we can harvest some linear ODEs in the UNs, and we can use these equalities here, which come from the fact that phi of 0 equals r0, as we can use these equalities as initial conditions to solve the UNs, and then evaluate them at theta equals 2 pi, and these values will be the focal values. Sadly, though, these are harder to find. We need a computer with purpose-built software, such as Maple or SymPy, to achieve this goal. Maple and SymPy are what are examples of a computer algebra system. For quadratic systems, we have a saving grace, the theorem of Lie, named after its discoverer, Chan-Ji Lie, and who published this article. And that sets down for the system 7, which works with only pure imaginary eigenvalues, the constants A, B, alpha, beta, gamma, and delta, and sets down some W scorings involving these constants, and then tells that if all of them are not, then the origin is the center. If there is one knotless, it's going to be a focus, and the sign of the knotless W will determine how steady this focus is. The proof of this theorem is based on this system, which has 7 parameters, into one with less, 5 or 6, I can recall right now. Finding the values of this new system, and then linking them with the W's of the original system by way of a multiplication by a knotless constant. Meaning, if we have the third focal value, we'll need to find an alpha 1 such that this focal value can be written as alpha 1, W1, with alpha 1, if alpha 1 different from 0. And the same for the fifth focal value in W2 and the seventh focal value in W3. This is all I have to talk about. I'd like to thank Dr. Claudio Aguinaldo Buzzi for overseeing the building of this work, and the São Paulo's Research Support Foundation for handing over a scholarship to me. This is the process. The thoughts, 4 steps, and findings questions brought here are my own and do not meaningfully portray for past vision.